Good morning. Today we're going to talk about Module 2, Lesson 3, Magnetism and Electricity. And in this lesson we start to look at how magnetism works and how it is related to electricity. In the last lesson we drew a model of how a junkyard magnet was able to pick up hubcaps and how the ones on the bottom were able to stick even if they weren't in contact with the magnet. So you went around your house and you looked at different metals. And you test them with a magnet to see if all metals are magnetic. And what you should have found out if you went to an aluminum can or you went to your musical instrument, there are metals that are not magnetic. The ones listed down with the red lines through them are the non-magnetic metals, and the ones that are magnetic that are naturally occurring on Earth are iron, nickel, and cobalt. Iron alloys and steel are both mixtures that have iron in them. That's why they're magnetic. But these three, iron, nickel, and cobalt, are in the iron triad. They're transition metals. So we know that these have some kind of iron, nickel, or cobalt in them because they're sticking to the magnet. But what they want to know is, why does the magnetism travel all the way down here when normally it wouldn't? If I just had a hubcap that was down here, this far away, it probably wouldn't pick it up. But once I have these stuck to it, it will pick it up. So they want to know what the possible causes are, and the whole lesson goes through possibilities and whether they are accurate or whether they're not. One of the possible causes for that is these metal pieces. Each hubcap is going to be magnetic or a magnet. Number two is the field is strong enough to hold non-magnetic metals. And possible number three is the magnet turns metal pieces into magnets. So they look at those and they start off with a demonstration of a magnet holding up paper clips. And this is similar to the electromagnet, where the magnetism is coming out of the pole and it would pick up this paper clip, but it probably would not be able to reach that far down and pick up this bottom paper clip. So they want to know what ends up happening if this paper clip is magnetic and can pick up that paper clip. What happens if you take away the magnet? So they're going to fall apart. They may stick for a little bit, but they're eventually going to fall apart because they weren't permanent magnets. So we need to know what a permanent magnet is versus a temporary magnet. And to understand that, we need to go back to the structure of the atom. Atom has three main subatomic particles: the electron, the proton, and the neutron. We know that the proton and neutrons are found in the nucleus in the center of the atom. In this picture, protons are green and they have a positive charge. The neutrons are red and they have a neutral charge. And around the outside in an electron cloud are the electrons, and they have a negative charge. We know the law of magnets says that opposites attract and likes repel. So the net positive charge inside the nucleus is attracting these electrons. These electrons are hanging around because of the net positive charge. The reason that some are closer and some are farther away is some electrons have more energy. These are in a lower energy level, the two that are closest, and the one that is farthest away is a little bit higher energy level. So if you take the atoms and you start to arrange them into groups, they are called domains. But since they have a charge, right, they have a negative area and a positive area, depending on how they're arranged, they can work together or they can work against each other. If I look at this atom and this atom, they're pulling in different directions, so they're going to cancel each other out. These two are pulling in different directions, they cancel each other out. Because it has such a random arrangement, this is what a non-magnetic material would look like. This might be glass, it might be paper, it might be an eraser, something along that nature, where there is no pattern to the way the atoms are put together as far as magnetic pull. In this one, they are working together. There's areas that all these are lined up and they're all pulling in the same direction. All these are lined up and they're pulling in the same direction. So these are called domains, where the atoms are working together and pulling in the same direction. But you still have kind of the same thing, where these are all pulling in this direction, those are pulling in the opposite direction. So these would cancel each other out, those will probably cancel each other out. So you still don't have a magnetic field around the outside. So this isn't a magnet, this is a magnetic material. a magnet will have domains. It'll have areas that all work together, but not only does it have domains, all the domains are lined up. And the more lined up they are, the stronger the magnet you have. So these would have a magnetic field because they're all pulling in the same direction. So this would be a picture of a strong magnet. This is a picture of a magnetic material, and this is something that is not magnetic. So if we apply that to a nail, we know that a nail has iron in it, so it's going to have domains, and this shows that the domains are kind of random. So I know that I can pick it up with a magnet, but it's not a magnet itself. So what happens when I take a magnet and I put it near this nail tip? The magnet will help to rearrange the domains. So instead of working against each other, it will line the domains up. Once the domains are lined up, then you have a north pole attracting a south pole, and this becomes a magnet. When you take the magnet away, it takes some time, but these eventually return to a random order. The reason the paper clips didn't fall apart immediately, they stuck for a tiny amount of time, is because these domains that were all working together went back to the random position. Another way that you can get domains to line up is through electricity. Electricity in a battery is direct current, and it runs in one direction. It comes out of the negative and it comes back into the positive. So as electrons with their negative charge go around the domains of a nail, they're attracted to the negative charge and they start to rearrange themselves. So if I have more electricity running through here, or I have more coils running through here, I'm going to have more domains line up, and I'm going to get a stronger magnet. Another place where charges are attracting and repelling is with static electricity. Static electricity is not magnetism, but it does have negative and positive charges. So if I take a balloon and I rub it on my hair, I am getting electrons and collecting them on the outside of the balloon. When I take that balloon and I move it near a wall, the electrons that are normally up here in a neutral atom are pushed away, and that leaves an area that is positive and an area that's negative. So the positive attracts the negative and they will stick together. Or I could take two balloons and do the same thing, rub them both on my hair, and then they're going to have the same charge. When they have the same charge, they're going to repel because likes repel. Opposites attract, likes repel. So if we look at the kid's hair coming down the slide, as the slide collects electrons from the little boy, he starts to get a positive charge. Each hair has a positive charge to it. It's going to start repelling each other. So the reason his hair is standing up like that is because, just like the balloons, same charges are going to repel, and his hair is trying to get away from each other. This also happens in lightning. When cold fronts and warm fronts pass by each other, electrons are transferred into the cloud, and you have an area that's negative and you have an area that's positive. As this comes across the ground, the same induction where the electron is pushed down and away creates positive areas on the ground, and when the potential difference between the cloud and the ground is high enough, the electricity will jump and it'll have a lightning bolt. It can also happen between clouds, where you have a positive area of cloud and a negative area of cloud, and there's enough static electricity built up that the static will be pulled from one to the other.